There is one and only one thing on this week's homework that you don't know, that I did not make a big dealio in introducing forces-yo. And that is that the acceleration of an object sliding down a ramp without friction is g sine theta. Bam, there it is. Write that down. This is in your lab. This is the entire purpose of this week's lab. But let me say it in lecture for the 3 people who aren't in lab this week. Acceleration of an object rolling down a ramp or whatever, sliding down a snowy hill, moving down a frictionless incline is g sine theta. G is 9.8. Theta is the inclination angle of the ramp. The biggest problem I have that students typically have with this is if I give you 7 degrees, what mode does your calculator need to be in? Sine of 7 degrees. So watch out. If your calculator is in radian mode, your homework problems are not going to be coming out, yeah? Watch out. Okay, you've been warned. There we go. And there's nothing else to those problems. If you know how to calculate the acceleration, it's an ordinary problem where, given velocity and acceleration, you need time, or given position, displacement, and velocity, you get time, whatever I ask for. It's the same skills we've been practicing for pushing a month. Today, though, I would like to continue on with our light and fluffy introduction, nice and easy peasy, haha, if only, introduction to forces. My 3 o'clock class did mostly great, except for one thing bit them hard. So I want to start off with a skill to practice avoiding getting bitten hard. What's the opposite of the dog bites the man?
Man bites dog.
Is it the man kicks the dog? No, the verb stays the same. You just switch the 2 nouns, right? The man bites the dog bites the man. Are opposites. You don't put in a new verb. What's the opposite of professor punches the student? Oh, well, there's a lawsuit. Okay, what is the opposite of professor punches the water sprayer? What do you call these damn things? The water spray bottle. The professor punches the spray bottle. The opposite of that is? Yeah, well, it's sort of silly, but yes, exactly. If I say that the professor exerts a normal force on the spray bottle, there we go. The professor exerts a normal force on the spray bottle. What's the opposite of that? Exactly. The professor exerts a normal force upward on the spray bottle. What's the opposite of that? Spray bottle exerts a normal force downward on the professor. Is the opposite of normal force weight force? No. No, the opposite force of normal force is normal force. If I push up on this sucker, it does not gravitate me. The earth gravitates the spray bottle. What's the opposite of that? The spray bottle gravitates the earth. There we go. The spray bottle gravitates the earth is the opposite of the earth gravitates the spray bottle. It has nothing to do with the ground supports the spray bottle. That is not the opposite of the earth gravitates the spray bottle, okay? Now let's see if that makes... It's easy when we say it in English. Let's see if this makes any sense when I put it on a slide. I'm hoping that that will forestall a bunch of problems. Issues. Questions. Whatever. Okay, so here is, we are revisiting, this time not in crappy handwritten notes. We are revisiting many of the topics that we did yesterday with more exercises where I can see how you're learning it. I get to start here with a little bit about the third law, because that is, in my experience and in the 3 o'clock section's experience, the hardest one. Let's talk about the third law. The nature of force, the nature of dynamics, the nature of what we're doing for the next month or so is interactions. We've talked about how things move. Now we can talk about why things move. They move because they interact with stuff. And I want you to count here an interaction is between one thing and another. How many things are there in that sentence? One thing and another, let's count them. 2. That's right. Not 3, not 1. Not 1. A force, an object can't push on itself. I mean, am I flying? Oh, please let me be flying. No dice. You cannot accelerate your center of mass by pushing or pulling on yourself. We'll talk about systems and internal forces towards the end of this lecture, and then that will become actually very important. Is it three things? No. Newton's third law of pairs, what we're leading up to here, the nature of forces, third law of pairs are always A and B, B and A. If you throw a third body in there, a third object in there, a third thing in there, you done did it wrong. Okay, so a big, 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 big problem that lots of people have. The Earth gravitationally pulls down on that roll of paper towels. The table, with a normal force, a support force, pushes up on this roll of paper towels. Are those forces equal? It's just sitting there. You can look at it. What's its acceleration? Okay, so are those forces equal? Does the gravity force and the normal force point in opposite directions? So the Earth pulls on the paper towel, the table supports the paper towel. Question B, are these third law pairs? You can just say yes or no, by the way. You don't have to type a complete sentence. Okay, time's up. Time's up. This is B. A was identifying a video game character. Okay, so the Google question C. How many objects did I just mention? Again, I talked about two forces, the force of the Earth gravitating the paper towels down and of the table normal forcing the paper towels up. How many objects did I just say in those two phrases? Put them on the Google form. See, can you count? I bet you can. Oh, no, there are lots of people who cannot count. Womp womp. One more time, I'm going to say the phrases again. Here are the two forces. They involve the Earth gravitating the paper towels down and the table normal forcing the paper towels up. How many nouns were there in those two phrases? The Earth gravitates the paper towels down. The table, the normal forces oh, for God's sake, paper towels up. How many nouns did I just count? Remember, a noun is a person, place, a thing, baby. Okay, there are three things. There are three things. There's the Earth, there's the paper towels, there's the table. Three nouns. Follow-up question D, are the two forces third law pairs? I ask again, are they third law pairs? They are equal, they are opposite. There are three objects interacting. One, two, three, four. If you are confused, read the slide. It is the very first sentence on the slide that I'm telling you the answer here. You can turn to your neighbor and discuss for a second. Okay, time's up. I got 2/3 of you. Third are still missing it. Okay, let's identify again. Third law of pairs, 2B third law of pairs. How many objects? How many objects are involved in the two forces I just described? Can they possibly be third law of pairs? No. If man bites dog, the third law of pair is not car runs over man. That's not a third law of pair. That's not the opposite. The opposite force to table exerts a contact force on paper towels is paper towels exert a contact force on table. You see, you just switch the nouns. Okay? If I am the table, I feel this pushing down. Not very hard, but still pushing down, yeah? If I am the paper towels, I feel a support keeping me from falling, right? That's third law of pairs. By the way, when you step on a scale, what does it measure? No, it does not measure your weight. It does not measure your mass. It measures how hard you push on it. Scales don't measure weight. Look, pick up the scale, squeeze it between your hands. Is it doing anything with your weight? No. A spring scale is it's a spring that is calibrated so that if you and only you stand motionless on the scale on a constant velocity, if you and only you are not accelerating with the scale, the force you are pushing down on it with will be equal to the force that the Earth is pulling down on you. And it deduces your weight. It does not feel your weight. Your weight is only felt by you and the Earth. It's a secret. Okay? Your weight force exists between dose objects and dose objects only, you and planet. This paper towel feels a weight force downward. Does the table feel its weight? No. The table feels the normal force it presses against the table with. The weight is an interaction between planet and towels. I can make the weight force, I could make the normal force of the table on the chair be, you know what, let me do this on this because this is easier. And I do not have big, strong muscles. I can make the normal force different from its weight by picking up the chair. When the chair was lifting, it was exerting a bigger force on the paper towel than its weight. The weight force was not acting on the chair. I'm not saying that didn't feel anything, but I am saying it was not party to the two-body interaction, weight force of Earth on towels, okay? To get questions right today, identify the two and only two objects interacting, name the force, say it out loud, and then switch the order you say the things in. To identify a force, here's the pattern I'm always going to use. I'm going to say the kind of force, the thing that causes the force, the thing that feels the force. You should write this down. The 3 o'clock section was really having trouble with this. Type, cause, effect. Or a silly way to say it is the type of force, the dealer, and the feeler. Yeah, it's memorable. What kind of, this is how I name a force. You can also just call it Bob, but in my Google form, what I want to see is if I ask you for the force I'm exerting on this table right now, you would say the normal force, that's a kind of force, of the professor on the table. Okay, so again, the type, the cause, and the effect, the dealer and the feeler. I push on the wall. Professor exerts a normal force on the wall. Google form E. What is the third law of pair to that, baby? Name it as I just told you to. Again, I claim that the first force is professor exerts a normal force on the wall. Tell me the third law of pair. Ready, set, go. Ow. Why did my butt hurt? What's going on? Someone told me professor and wall. Someone told me normal force. That's not what I asked you to do. 3 parts to naming a force. Type, thing that makes the force, things that feels the force. Again, I'm not looking for 2 or 1 thing. Please tell me 3 things. What kind of force? What is causing the force and what is feeling the force? This is the third law of pair to the following force. Here's the first force. Professor exerts a normal force on the wall. Now switch the nouns around and tell me. Tell me that again. Google form E. Again, normal force that the professor exerts on the wall is what I'm giving you. I want the third law pair to that. Don't tell me the same thing that I just told you. Professor pushes on the wall with a normal force. Flip the nouns around and tell me the same phrase. Gravity is not the correct answer. That's like saying the man bites the dog, then the dog kicks the man. That's a different kind of force. If I push the wall, gravity is not the result of that, or the opposing force to that. The opposite of that. Okay, so we're at about 80%. I'd really like this to be straightforward. Write this down on your scratch paper. Type of force, dealer, feeler. Put a little space underneath each. Here is the original. I'm going to say a phrase and I want you to identify what the type, dealer, and feeler are. Ready? The professor exerts a normal force on the wall. What type is that? What is the dealer? What is the feeler? Great. Easy peasy, lemon squeezy. Great. Now write the third law pair, second law, the third law pair to that. Flip the nouns. Instead of professor on wall, say wall on professor. It is the same kind of force, just instead of A pushing B, B is pushing A. And you may resubmit this for E. Professor Hand is not a sufficient answer. Professor Hand, gravity is not correct. I just walked you through how to do every third law problem. I get lots of different responses. Again, the question for E that I'm asking is to identify the third law pair to the force of professor normal force on wall. The professor exerts a normal force on the wall. What's the third law pair to that? All you have to do is switch the dealer and the feeler. This is E. You can edit your E. I'm hoping this is E. No, I'm hoping this is EZ. The correct answer for E is the wall exerts a normal force on the professor. Again, what's the opposite of professor? Normal wall? Wall, normal professor. Okay. Question F. Question F. Let's test this. Let's test this hypothesis here. Why does that fall? What object pulled it? What is the object that felt that? Third law, pair that for me. The Earth pulls gravitationally on the paper towel. What is the third law pair to that? This is a Google question. Two words is not sufficient, my dudes. Please listen to the instructions. I'm looking for a phrase that includes three things. Drei Dinge. Tres cosas. I'm out of languages. Three things. The kind, the thing which causes the force, the thing that feels the force. You cannot do that in 2 words, please. Again, the scenario that I'm asking you to flip is to say, if the planet exerts a weight force on the towels, I want you to identify the third law pair to that. And you must tell me all 3 parts. The kind, what exerts the force, what feels the force. Still missing about 24 people. Okay, practice with me again. Man bites dog. Opposite is Earth gravitates paper towels. What's the opposite? Exactly. The third law pair is just the opposite perspective. Is the normal force got anything to do with that? No. Now, right now, the normal force is upward, whereas weight force is downward. The normal force is equal magnitude to this sucker's weight. Sure. Are these third law pairs? They're different kinds of force. What's the third law pair to the table, normals, the towels? The towels. The normal force on the table. Exactly. What's the normal force to the gravity, the earth, weight forces, the towels? The towels weight force the earth. Exactly. Now, is that weird that the paper towels are gravitating the planet? Yes. Yes, I accept that's weird. We don't see that. We don't see the earth fall up to meet the paper towels as they fall. Why? The weight is exactly equal. Weight is the force. The weight force that this exerts on the earth is the exact same force that the earth exerts on this. The what? Ding, 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 ding. It's probably what you were thinking about. Okay, so what does mass have to do with it? Exactly. Go flick a sumo wrestler and flick a BB. Same force, big mass. Does that recoil? Well, I mean, theoretically, an insignificant amount. The Earth is 30-something orders of magnitude, one with 30 zeros after it, more or less, bigger than me or the paper towels. So it recoils 30 orders of magnitude less. What equation connects those things, mass, force, and motion? What equation did we just learn yesterday class? Acceleration is total force divided by ding, 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 ding. If mass is really big, acceleration is small. Great, now let me say the same thing several times and see if this has clicked. Here's a way of putting the third law. Note how many objects there are. One object on a second object, the second back on the first. You cannot introduce a third object. That is not part of the third law. It is not guaranteed that other forces exerted by other objects will always be equal. Third law guarantees that if A pushes B, B pushes A. I don't know about C. Hammer exerts a big force on peg. Earth supports peg with a friction force. Planet pulls gravitationally on both of these. Which is bigger? The force that this pushes the peg down or the force that the peg opposes the hammer with? Shout it out. Let me hear you. No, Google form it. That way I can scan it. Which is bigger? The force that the hammer pushes on the peg with, this is a normal force, peg on hammer, or normal force of hammer on peg. Which is bigger? Google question G. If you are confused, also you can read the slide. Correct answers. A paper towel is not part of this question. This is G. I know I've been talking about paper towels, but please try to focus here. Okay, again, we've got a couple dozen people here. Let's work on this. What's this word say? Which is bigger? Neither. It's a trick question. Okay. Is that weird? Why doesn't the hammer spring back? Why does the nail move but not the hammer? A big bout. Two reasons, actually. One is the hammer's bigger than the nail. What's the second reason? There's more than one force acting on this sucker. Acceleration is not just any old force. Acceleration depends on all forces together. So you can't just say, I will give lots of problems where there is only one significant interaction force, but you can't just say that. For instance, if I asked you about the acceleration of an object given a force, you can't just say that it's equal to the other sucker's acceleration. You have to look at what else is applying to it, what else is acting on it. So two reasons. Two reasons. I can count. Yeah. Okay. But they're equal. Which direction does the peg push? Point with your fingers, everyone. Point with your fingers. Which direction does the peg oppose the hammer? The hammer is pushing down on the peg. The hammer is pushing down on the peg. Which way is the peg pushing on the hammer? The peg pushes upward on the hammer. That's right. Good. Think about this. Likewise, the hammer was moving downward, negative velocity. Then it's not moving, zero velocity. What is the change in velocity? Is that a positive or a negative number? Google form. Google form. If I go from initial negative to final zero, what is the direction of the acceleration? Google form H. Again, initial velocity is negative, final velocity is zero. What is the direction of the acceleration? I've had several requests to add these slides to Canvas. As I said at the beginning, I said, I am still locked out of Canvas because my phone has not yet arrived from Verizon. I will do it as soon as I can get in. Hey, okay, that's more like it. Okay, again, we're looking at the change formula. If we start with an initial equals negative and a final equals positive, we start V initial equals negative something. V final equals zero. It goes from downward motion to at rest. The change in velocity, the numerator for the, let's say -5 meters per second. The numerator for acceleration is final minus initial. And if I subtract a negative number, what do I get? Positive number. So the correct answer for this, reflect on this, if I go from moving down to not moving, that's an upward acceleration. That is a positive change. Negative becoming zero is a positive. What do you have to do to your bank account if you're in debt and you want to get to zero? You have to add money. You have a positive change. Don't Yeah, let's move on. Okay. Google form I. A, B, C, D. You don't have to write the whole thing out. Good, good. No, mostly good. No. Good. Positive is not the correct answer. My dudes, you gotta read.
B. One percent. Wait, what did you do? What? Yes, to me.
Are these third law pairs? Ball, kick, foot, foot, kick, ball. Are these the same thing from a different perspective? What does the third law guarantee? B. B. They're in my eyes. B. Correct answer is B. And again, what's one reason why the ball goes flying and hopefully the soccer player does not? Less mass, equal force, more acceleration. More mass, equal force, less acceleration. Good. I'm going to skip action and reaction. Whenever you see the word reaction, I want you to replace that in your mind with third law pair, the opposite force which is guaranteed to exist by the third law. Okay. Focus, focus. When I say when the text says reaction, I want you to imagine what I will say consistently and put on your tests is third law pair, the force which is guaranteed to exist by the third law. Huh? Yeah, exactly. Google Form J. Let's go for 100%, y'all. So far, so good. So far, so good. When you're done with this, turn to your neighbor and ask them why. Question.
What would it be like that? 1940.
40s? Why the 40s? Oh, 1660s is when this stuff was discovered. Yeah, this is Newton, Isaac Newton. And actually, well, no, actually in the 1400s is when this principle was first suspected by Descartes, although he didn't prove it. But anyway, sorry. Think about explaining this for the first time? Oh yeah. Breaks people's brains. Still hard. Okay, let's identify this. Let's identify this. Earth pulls you down. What manner of force does Earth use to pull you down? Gravity. What's the third law pair to Earth gravitates you? You gravitate Earth. Correct answer is C. We're now at 90%. I'm going to move on. Okay. If this is breaking your brain, email me or Discord me or office hours or Venmo me. No, you don't need that. Seek the answer here. There's a pattern here. I'm not going to spend more time on it though. Yes. One question and then we're done. Shh, can't hear. No, need them all. But it's the one that was breaking at the start of this 75% of the class, and it's still breaking 10% of the class. It will absolutely be on the test. Multiple questions on the test. Once this clicks, though, it's free points. Strive for it. Okay, we're moving on. Cannon shoots a cannonball. I want to emphasize this. A cannon shoots a cannonball. This is a third law pair. The explosion of gunpowder pushes cannon and cannonball equally. The Newton's second law formula, the only formula you've got right now, well, there's weight, but whatever. The only law formula you've got is acceleration of an object is force of the total force on that object divided by that object's mass. I want to write this out with bold letters here for a second to emphasize. If f is the same, if the numerator is the same for two fractions, which fraction is bigger? The one with the little m or the big M? The little m. If I divide by a smaller number, I get a bigger number. Do you guys know the story of the third pounder? Okay, Burger King lost a lot of money in the 90s, I think. I don't remember. Lost a lot of money because they went out competing with McDonald's quarter pounder by selling a third pounder. Failed. Focus group showed that people thought since 3 is smaller than 4, a third is smaller than a quarter. Significantly more people. Don't be them. A third is this much, a quarter is this much. So if I divide by a small number, a cannonball has a small mass, gives a proportionally bigger acceleration. A cannon has a much bigger mass that gives a proportionally smaller acceleration. Inversely proportional, I should say. And again, let's relate this back to common sense. Suppose you flick a mosquito. Let's talk a BB. Flick a BB, then go flick John Cena. Big mass, small acceleration, and punch in the gut. Little mass, big acceleration, yeah? Also, presumably the cannon is fixed to the ground. Like that sucker should be pegged down with a big peg. But Newton's third law, even if the cannon were on ice, Newton's second law guarantees that the cannonball is still going to be moving faster away. Read carefully. No, we're going to do this. Google Form K. Read carefully, please, and think about what you're putting. And then turn to your neighbor and argue. Your neighbor is a dad? Is dead. You're dead? Is he undead? Someone cast turn undead. Let's find out. Okay. Read carefully, by the way. Read carefully. So far, so good. Okay, you could just put A, B, C, D, yo. Just put A, B, C, D. You don't need to write the sucker out. Question. That'd be a rough time for the shooter, yeah. But the center of mass of the exploding glass would still recoil less. Yeah. What? Parlak from Baldur's Gate 3. Also known as Best Tiefling. Tiefling? Devil. Tiefling. Whatever. Okay, yeah. Yeah, we probably shouldn't. Okay, la respuesta correcta. Masses are different. I want to emphasize A and B cannot be true by which law? The third law. A is not true because the third law doesn't just apply at different times, it applies at every time. And I'm testing the same thing again, but I'd really like to get more than 90%. Question L? Good, 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 bad, good, good, good. Much better than 3 o'clock. Bad, bad, bad. Good, 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 bad, bad, good, good, good. Bad. Okay, rough estimate, we're at 90% here. So again, I'm moving on. The correct answer is it's the same force. This is a third law pair. Bug splats on windshield, windshield splats bug. It's the same force viewed from a different perspective. The force has to be the same. Now, the follow-up question is why doesn't the window crash in and wreck the car? Let me ask you for this. How hard do you have to push to shove a car out of the way versus how hard do you have to push to squish a mosquito? The same force has different effects, but that doesn't mean the force isn't the same. The squishy force is like this much. Doesn't take much to squish a mosquito. Don't confuse the result of the force for the strength of the force. If the two objects are interacting with the same kind of force, A pushing on B, B has to push on A equally. I just answered my own question there. Yeah? No. Yeah, sure, here. Okay. Question M. I know I'm harping on it here. Please be patient if this is clicked. Think carefully about what you're answering. I will give a hint that this is this problem proved very spicy for 3 o'clock. Okay, again, one more time. When I give you a multiple choice question, I'm just going to tell you, stop typing out the answer. A, B, C, D, please. I have said this like 15 times. Listen to instructions, please. You may carry on.
If you like guess what already. I know.
Twice as many people are right as the 3 o'clock class. 3/4 of the 3 o'clock class were wrong on this. Turn to your neighbors. Turn to your neighbors, and I want you to high five, but only one person moves their hand, okay? So one person holds their hand up, and the other person moves their hand in. The one person does all the muscle work, okay? You could do this to yourself too, it doesn't really matter. Now switch roles. The other person holds their hand still, and the first person extends their arm. Okay, so force is like the sting in your hands. Did it make a difference which hand was moving? Did you feel a different sensation in your palms, the stationary one versus the moving one? It doesn't matter whose arm moves. It's a third law pair. Third law says nothing about if A pushes B, B pushes A, but only if A's arm is the one moving. It's a third law pair. The forces are always equal. It doesn't matter who is extending. It is impossible to push differently. Do I love my son? Yes, but only if he cleans his room. Is the answer to that question true? Hint, hint, I'm not a terrible person. Well, I am, but not for that reason. Okay, the correct answer here is A. It is impossible for two things to push on each other where one pushes in a different way. Okay, if the forces are equal, and as it says, masses are equal, what can you conclude about their motions? They are equal. Okay. Twice as many people got this right in this section, but that still is 60 people missing this. Please turn to your neighbor and explain in detail, in your own words, both ways. Teach each other this. My words are not the only way to put it. Use your words. Why is the answer have to be A? All right, time's up. Question me, argue with me, engage with me. I mean, I'm already married, but engage with the concepts rather. Okay, really? Nobody? Yes, please. If you have the same initial velocities, accelerations, you have to have the same final velocities. Well, opposite directions, but same final speeds. And wait, was the question about, say your question again, say the last part. I want to make sure I'm answering the question you're asking. Yes, two people standing on ice, pushing off against each other, accelerate each other. And if they have the same force and the same mass, they have the same acceleration. They're both standing there, they have the same initial velocity, same acceleration, same initial velocity, same final velocity. Great. Great. One more analogy. Do you guys know what checks are? Like a bank gives you.
Yeah.
Okay. Not everyone does. I mean, I can't remember the last time I used one. Forces are checks. Forces are checks. If I write a $200 check to my butler, his checking account had better go up by $200 and my bank account had better go down by $200, right? That's the way money works, or at least should work, okay? So is it possible for his bank account to go down only if I write a certain kind of check? No, his bank account always increases the same amount my bank account decreases. This is the third law. Money of money, yeah. Again, I think we're at the appropriate place. Now I'm moving on for realsies this time. I mean it. When do I not use the third law? When forces are internal to a system. Thank you for asking. Let's make an example. Consider my child who has been turned by a witch into an orange. He is sitting in his favorite cart, and I pull on him with a rope. By Newton's third law, the force that I exert on the cart is equal to the force the cart exerts on me. Do those cancel? Google form, question L, do those cancel out? They are equal, they are opposite. Question N. Do those two forces cancel out? I claim the force that I exert on the cart is equal and opposite to the force that the cart exerts on me. Do those cancel out? Yes or no? I'm going to talk about the object under study. What we are focusing on, the system in question, is kid in the cart. The kid in the cart. That's why I drew a dotted line around it. Okay. So if you want to find how the kid in the cart moves, I claim that there are two forces. I pull cart pulls back on me. Do these cancel? And the correct answer is, well, one is you can try it yourself, and two is no. Listen very carefully to the words. The force that I exert on the cart and the force that the cart exerts on me. If I'm just talking about the acceleration of the cart, do I need to care about forces that aren't acting on the cart? Again, if I am asked for the acceleration of the cart, do I care about the forces that act on other things? No. If you've got the system is Nalo in his cart, then you don't care about what he does to other things. You only care about what is done to him. This is not cancellaceous. Do not cancel this. There is a third law pair, but I don't care about it because it's caused by the system, not on the system. I could use F equals ma for this situation, and I would only use one force, the tension force. Question me. No. That is a wonderful example of inertia, but that's not what I'm talking about here. I'm talking about whether third law pairs cancel if we consider, I push you, you push me. That's the third law. If I'm looking at just my motion, I don't care about you. I mean, I care about your emotion, but not physics-wise. I only look at forces on me. Question? Sure. Okay, so again, if my object under study, what I call my system, where I've drawn my dotted line, is Nalo and his cart, I am pulling Nalo and his cart. I exert a force on him. Sure, that's true. Yep. And by the third law, the pull of professor on cart is equal to the pull of cart on professor. Those do not cancel. Here, again, the second phrase, the force of cart on professor. I don't care about the professor. Well, that is true. If I'm talking about the cart, I only care about forces on the cart. You don't have to consider what the cart does, only what the cart feels. If I'm my butler, who cares that the professor's bank account went down? I got money, woo! Doesn't matter if I'm the accountant for the butler, then I don't care who gave me money. I only care that my bank account got a deposit. Question me. Very good question, which leads to my next slide. If I define system as kid and grown up, suppose we're on ice. Suppose there are no other external forces. I pull Nalo on a rope, he moves towards me, and I recoil towards him too. We don't change our center of mass. I cannot get to shore on a frozen lake. I can't get us both to shore by pulling him to me, right? So if we are exerting forces on each other, we can't move our center of mass. Now, I don't pull my son on his cart over frictionless planes. What we're going to see in half a second is there's an external force acting on Apple, on Professor, on whatever, acting on me. That external force is external. So if I were doing F equals ma on this system, this mass, then I would use this force and only this force. Internal forces cancel. The force of left on right, the force of right on left, that still forces on pieces of the system. They can rearrange your system, but they can never move the center of mass of the system. You don't like that? Ask me a question. You're frowning. Oh, that's allowed. Did you have a question? They don't cancel out on the previous slide because I don't care about myself. I only care about the cart. If the system doesn't include me, I don't care about me. Don't consider forces on other objects. So you're the apple, okay? That's impossible. You cannot pull a cart harder than it pulls back on you. Third law. You pull on the cart at all and it rolls. The ground pulls on you. Bigger than the rope pulls backwards and you move. If you do this, imagine doing this on ice skates in a cart. Are either of you going anywhere? I might pull Nalo to me. I might pull myself closer to him, but we're not moving anywhere. So the internal force can rearrange the objects about their common center of mass, but the force I care about here is external forces here, my traction on the ground. With no external forces, there's no acceleration of the system. Okay, so again, say I exert 100 newtons on him and the ground exerts 100 newtons on me. Yeah, right? Can you imagine that? How fast are we accelerating? He's 1 kilogram and I'm 1 kilogram. Again, he's 1 kilogram, I'm 1 kilogram. I exert 100 newtons on him, ground exerts 100 newtons on me. What happens? Okay, so I exert 100 newtons on him, right? Right? And he's 1 kilogram. How fast does he accelerate? F equals ma. Solve for a. 100 divided by 1 is 100. He accelerates at 100 meters per second squared. Ooh, that's actually bodies start breaking at that speed. I'm not actually swole enough. He's also not 1 kilo. Okay, the ground exerts 100 newtons on me. Hey, how hard am I pulled backwards by the rope? If I pull Nalo with 100 newtons, he pulls me with, what's the total force on me? The ground is trying to propel me. Nalo is trying to oppose me. Those are opposite directions. That's not adding. That's opposing. If I'm pulling Nalo, that means that I would have to have extra force to accelerate myself. This is an impossible scenario. If he's accelerating, I would have to accelerate too, but there was a net force on him and no net force on me. It's impossible. The ground has to push the system harder because there's more mass in it. He only has to get pulled by a medium size force. The whole system has to get pulled by a big force. F equals ma. If you got more m, you have to have more f. This should probably be done with you doing lots of homework problems, solving increasingly sophisticated scenarios like this. That's not this week, but I'll take questions here. Yes.
Okay, so when Apple is pulling the orange,
Mm-hmm.
so putting its weight and the
No, the apple does not pull weight. So wait, hold on. What kind of force? What is causing what is feeling?
Apple is pulling the orange
Mm-hmm.
situation.
With the rope is a tension force, is what we call that.
Dealer is Apple,
Uh-huh.
dealer is orange.
Uh-huh.
What my question is that if Apple is pulling the orange, it has to exert a force to pull itself and the orange, right?
What pulls itself? I can't pull myself.
Okay, so
What is the force that's moving me forward? What is causing that force? How do you walk?
like
No, your legs are part of you. Your legs don't push you.
ground push.
The ground, yes. So the apple doesn't exert a force on itself. The ground pushes on the apple. And the net force, the ground minus the tension backwards, must be greater than 0. Otherwise, the apple can't move forward.
is is dealt by the ground.
Mass of the apple.
So
Mass is not a force.
when the apple is pulling the orange and moving forward,
Mm-hmm.
all the M1 plus M2.
The ground must accelerate m1 plus m2. The tension must only accelerate m2. Yes, good. What I just said there, that's beyond the scope of what I will give you homework next week. That's beyond the scope of what we're leading up there. We're going there, but that's not on the test yet, that level. Being able to actually solve the equations for multiple bodies. There's one more point I want to make. One more point and one more point only, which is good because I only have a couple of seconds left. OPQ. Talk to me about a block of ice on an inclined plane. What force do you think remains constant, if any? Does N means normal force? Does the support force change? And when I reach verticality, 90 degrees, what is the net force on the block? I had a whole bunch of people tell me 9.8 meters per second squared in the last class. I'd like to emphasize that meters per second squared is not a force. Looking for an algebraic expression that allowed me to calculate the net force on the block. TLDR, for Q, tell me force, not acceleration. It says force. This will help you in your lab if you haven't done your lab too, thinking through this. Good, 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 bad. What is that? 5% bad? Good, 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 good. Ah, God, there's only one wrong answer here so far. No, 2. No, 3. No, 4. Still, 30 correct answers, 4 incorrect answers. All right. But everyone, put your, still working. It's okay. Ooh, you guys are way better at this part than 3 o'clock. Good, good, good. Correct, 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 correct. Whew. Whew. A squared plus b squared equals c squared is not a sufficient answer there. I mean, yeah. I'm going to zoom in on the diagram here and emphasize that last class I told you how to calculate weight, the formula for weight. And the formula for normal is, there is no formula, you have to deduce it. Okay, so in particular, question C again was, in the vertical case, what's the net force on the block? Oof, oof, oof. Char. You should be. Okay, so O and P hints, answers here. O, weight. P, decreases. Here's how to reason through these. Does the planet as a whole, gravity, the magnificent extension of our planet through invisible strings of force, does that care any bit at all what you're doing to a ramp? Weight is weight is weight is weight. It's mg, baby. That's it. That's all it'll ever be. Eventually, you'll learn how to calculate g on different planets, but for any given planet, and lifting this ramp is not changing the planet, mg is mg. It does not change. P, the magnitude of n changes. Consider this. At the beginning, you're completely supporting the block. When it's just falling next to, is the ramp pushing the block at all? Even a little bit? No. There is no normal force when when the block is just sliding beneath the ramp. It decreases. Now, the thing that I'm seeing about 5% are right on is Q. Reflect on this, my grasshoppers. Reflect on this. If the normal force goes to 0, there is no normal force. I want you to find the total force on the block if the normal force goes away. Write this down. Think about this. If there is no normal force, can you find a mathematical expression for total force? F net would be, you can edit your answer for Q. I'll tell you the answer in 3 minutes. Better. Good. No. No. Yes. No, 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 no. Yes, no. There is no equation for normal, not there is no equation for net, my dudes. Yes, 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 yes. N plus negative mg. Gravity pulls down.
That is why it's still ambiguous.
Okay, the answer for Q is negative mg. I take away the ramp. The planet hasn't gone away. Okay, if there's a planet nearby, here's one of the rules that we'll focus on when solving force problems big time after the exam. If there's a planet nearby, include a weight force. You all better have a good weekend, or else. Question. 9.8 is the amount of force that each kilogram gets pulled. That's just G. The force is mg. Weight and acceleration and gravitational field are different. And properly negative, it's downward. Sure.
It's these packets with a midget.
Yes.
Got it.